Hello and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor, and I'm delighted to welcome you to a webinar session where we will learn how WL Gore uses definitive screening designs to analyze multiple factors and optimize their production processes. I will introduce our speakers, who you can hopefully already see on screen in just a sec. But first of all, just to let you know about the software we're using, GoToWebinar. This is a platform that allows you to interact with our speakers. It's not just a broadcast. We do really want to see your questions. So in the GoToWebinar panel, probably down towards the bottom, you will find a questions box. Any question you have at any point throughout the webinar, just type it in there and we will do our best to put it to our presenters as we get towards the end of the presentation. Now, it's not just a presentation today, we're also seeing a live software demo of JUMP. And JUMP is the tool that can be used to do a proper design of experiments approach in order for you to optimize your processes and make sure that you are getting the most out of all of the processes that you evolve. So today, as I said, we're looking at how WL Gore uses definitive screening designs. Now, you will be able to watch any of this again. There will be a recording made available to you. We'll send that out in an email in a few days' time. And so if there's anything that you miss or anything that you would like to just go back and watch again, then that recording will be available from here on in. So do just keep an eye out in your email inbox for a copy of that recording, and you can catch up on anything that you weren't quite able to catch first time round. Now, also as a big thank you for all of the people who've attended live, you will get sent a certificate of attendance. That will be in the same email. Just give us a couple of days to sort out all of the admin with that, and you'll get a certificate that should land at the same time as the recording. Just a little thank you from us. So yes, do keep your questions coming in. Anything, no matter how big, how small, there are no stupid questions. And I'm sure that there'll be lots that you'd like to ask about how you can apply this approach to your own processes to make sure that you are performing optimally. So today we're going to learn how design of experiments created improved process understanding for WL Gore. We'll achieve faster and more targeted experimental product development, and we're going to help understand how design of experiments helps subject matter experts to make decisions based on data. Now that's your own decisions, but also it will help you to communicate decisions further up the chain and make sure that you get buy-in across your entire business using strong backed up data with a design of experiments approach. So our two speakers today, Valérie Nedbal, who is Senior Systems Engineer for JUMP Software. She's based in the Global Technical Enablement Team at the SAS Institute in Heidelberg, where she works closely with customers on software knowledge and implementation. She's got a PhD in molecular biology from the German Cancer Research Center, also in Heidelberg. We'll also be joined by Maria Lanzerath, who is Global Head of Statistics for WL Gore. She leads a global team of statisticians there, working with scientists and engineers to ensure that statistics are embedded throughout the manufacturing process. Now we're going to start off with Valérie, and she's going to kick straight into a live demo, after which we'll see some more presentations, some more live demos. We've also got a poll where we get to learn a little bit more about you and your own experience. So once again, any questions you get, and I've already seen some greetings from the Philippines, from Jeremy in the questions, so any questions, any comments like that, get them in there, and we will do our best to get back to you all, put them to you towards the end. So Valérie, thank you ever so much for joining us. I look forward to seeing your presentation and look forward to seeing the software in action.
Thank you, Ben. So can you see my screen?
We can, yes, all looks good.
Okay, so thank you for your nice welcome. Yeah, and welcome to the webinar, Optimizing Production Processes with Design of Experiments, also called DOE, and that will be followed by a case study presented by Maria. In this webinar, as already been mentioned, you will learn how to create, or how DOE will help you to create improved process understanding, how to achieve faster and more targeted experimental products development, how they can help subject matters experts to make decisions based on data. But I think what is really nice, and most importantly, how DOE helped WL Gore to save substantial amount of money and time by quickly identifying the real process drivers and hence a successful process setting, and optimize their process with a minimum of experimental runs that led them to build a robust process that is still in use. But first of all, let's spend some time by explaining what is DOE all about and why it is important. So what is a typical process? So in a process, many input factors are involved affecting the outputs. And ideally, you would like to maximize yield and to minimize costs. And therefore, it is important to understand the relationships between the output factors and all those responses in order to produce sustainable and robust products and process. And a common approach is one factor at a time, or OFAT experimentation. So consider experimenting one factor at a time to determine the values of temperature and pH that optimize the yield. So in an OFAT approach, you would keep one factor constant, like for example pH, and vary the other. Let's consider this scenario where you might leave pH constant at a certain level and vary temperature at different time points. And then you will find at a certain level of temperature one optimum. And consider to work with this level of temperature for the next round. So at the second round, you would leave temperature now constant and vary pH at certain time period. And you might find then maybe another optimum. But what is wrong with this approach? There's a lot of white space left and a lot of unknowns resides in this case. So do you think that you have found the optimum? What about other possibilities? Later, we have learned that a higher yield could be obtained at lower temperature and higher pH and a significantly lower cost process. So that would be one factor at a time. Let's consider now design of experiments. And I have here also one example of that. And here I have here an example where we have again pH and yield, pH and temperature, and then where we then gather the measurements of yield. In this case, you can see that at each run, we vary temperature and pH. And this types of approach provides a much more efficient and effective way to investigate relationships between factors and responses. Where I already said, you vary the factors at each experimental run and use the entire design space without omitting any unknowns, as you can see here. And you can see here where your runs are. So for example, run 1 would be here in the middle, run 2 would be here again, here in the middle at the top above, run 3 would be here in the middle on the bottom, and so forth and so forth. So at each of the run, you vary your different factors each time. And you might then find an optimum of the yield here, for example, again at the left top of the corner of the design space. So if you compare the two different methods, one factor at a time and design of experiments, you might maybe conclude that one factor at a time looks maybe simple and the design of experiment looks maybe more complicated. But design of experiment is much more rigorous and fully balanced factors. And one factor at a time, it seems maybe logical and it's easy to analyze, but it requires much more runs as you would compare design of experiments. Also, what is very ineffective in one factor at a time is that you misses optimal settings of factors. In design of experiments, as I said, it's much more rigorous to find an optimal settings of factors. It can find also interactions in design of experiments and also quadratic terms that is not really possible by using one factor at a time. And ultimately, by using design of experiments, you will find best process, as in one factor at a time, you won't find the best process. So what would be the traditional approach of experiment method is what we are calling an iterative way of doing design of experiments. First, if you don't know anything of your process, you might screen first your factors by using screening designs to identify the few really significant factors out of a very large number of potential candidates. And once you have screened your different factors, you might switch or you might augment your screening designs by studying interactions in addition to main effects and build more comprehensive models like factorial 2K designs. And also what is very, very common is using RSM or response surface designs to describe quadratic effects and identify optimal settings. So maybe there are some terms that are maybe not familiar, like interactions and quadratic effects. So what is an interaction? And I have here an example that I have put here also on my presentation. So what is an interaction between two factors? So an interaction effect occurs when the effect of one variable depends on the value of another variable. So I have here a very, very simple example where where I have put a regression of two factors on oxygen uptake versus runtime. And if you see something like that, where you can see the regression of those two factors compared to two genders, like woman and man, you can see that the slope is different. And in this case, we can already say there is an interaction between the gender and those factors. You can also see that if you build the model by using the profiler, and we will use the profiler quite a lot in this presentation, where you can see again the oxygen uptake depending on the runtime. And here we have also a profiler of the gender. If I switch from male or from woman or from man to woman, sorry, you can see that the slope is different also between the two different genders. So we can see, and this is what we are calling an interaction, is that the effect of one factor depends on the value of another factor. What is a quadratic effect or a nonlinear effect? It's what you can see here, maybe quite, yeah, I would say a very, very important quadratic effect is that it is an interaction term where a factor interacts with itself, and it is a nonlinear effect. And if you have a such relation by a curve, and if your quadratic effect is very strong, as here in this case, then you can say that the optimal level of your factor are not in the extremes of the experimental region, but inside it, like here. So having those different terms or those different effects in mind, this is where really the beauty of the definitive screening designs are. And let me introduce you again what is definitive screening designs, or DSD. So again, I have here an example where I can explain you what are the properties of those definitive screening designs. Here's an example of an experimental design of 6 different factors. And you can see that those DSD have, or each factor have 3 levels. It means you have a maximum and a minimum level here. You can see 1 and -1 and a middle point. And that's what we are calling a 3-level factor design. What you can also see quite visually is that each pair of runs is a mirror of itself, and that's what we are calling a fold over. And those different properties of those runs is very nice in different ways is that you can estimate linear, nonlinear, and quadratic effects by one design. So you don't need to do 2 or 3 different designs. You can estimate already quite a lot of those effects in one design. And also DSD allows to study the effects of a large number of factors in a relative small experiment. Again, by reducing the number of runs will allow you, by using those types of designs, to estimate a lot of different effects. So not only main effects, but also quadratic effects and interactions. And again, I have a small example. And afterwards, after this example, I will leave Maria to explain her case study. Again, I have a quite simple types of example where we will build a DSD or definitive screening designs with 7 different factors. So we have here those factors: stir rate, feed rate, time, modifier, temperature, humidity, and CO2. And we want now at each of those runs to vary all those different factors in one time. So how, and of course you have an objective, and the objective is the output factor or the response. And let's imagine that our objective is a type of reaction that we want to maximize. So how would you build a DSD using JUMP? So the DSD is under the DOE menu, of course, and there you have definitive screening designs. So if you open the definitive screening designs, here is where you will have the ability to enter all your different responses if you have more than one, and all your different factors. So in our case, we want now to build a design with our reaction, for example, like that, with a percentage. And the factors, we want now to have 7 different factors. So if you have already your factors already in your open as a table, here as it is here, you can simply ask JUMP to load your different factors. And we have them here. So we have here over 7 different factors that are already now embedded in the definitive screening design. And you might continue in order to build now your matrix with no blocks in our case, and we don't want to have extra runs. So we will make the design, and now JUMP will make a 17 run experimentation design, where you can see at each of your experimental run, all your different factors vary at each time. And again, the beauty of those DSD is if you are interested to find if you have some confounding problems or correlations, you will find here in the design evaluation a color map on correlation, where you can see the correlation between different main factors, as you can see here, and also correlation between all interaction terms and main effects. And you can see here, if you read now this correlation matrix, you can see everything is white. And the white means that you have no correlation between all those different terms. But you can see that some of the higher terms might be correlated between each other, but you will still be able to estimate some of them. So we have run this experiment, and let's see what we can find. What would be, if you build now the model, once you have run all those different experimentation, you can fit your definitive screening design, and then you will find your main effects and also the second order effects estimation, if they are significant or not. And you can already see that from the 7 different terms, only 3 are significant, like time, modifier, and temperature. You can make the model or run the model. And if you run the model, you will find again the effect summary with all the effects or with all the terms that are considered as significant. And you can see that 3 of those terms are not significant, so you can remove them from the model, not to have only one simple model with all your 3 different factors. And you can see that we could estimate a quadratic effect or a nonlinear effect of time, and also strong correlation or strong interaction between modifier and temperature. And as a last piece is now to ask JUMP to find the optimum by using the desirability function. And as I've already explained, we want to maximize the desirability, and JUMP will find, or the model will find, the optimum level of your different terms in order to have the maximum of your reaction. So by this, I will leave now the words to Maria, who will then explain her case study. Thank you.
Thank you very much, Valérie. So we'll hand over to Maria now. Just in case you weren't here at the very beginning, Maria Lanzerath, Global Head of Statistics with WL Gore, leads a global team of statisticians to ensure that statistics is embedded throughout the manufacturing process. So thank you, Maria, for joining us. And once again, if you have any questions, get them in at that questions box at the bottom of your GoToWebinar panel. We should have some time at the end of the presentation to put those to our guests. Thank you, Maria. Take it away.
Yeah. Thank you, Ben. Thank you very much, and a warm welcome to everybody. My name, as you know already, meanwhile, is Maria Lanzerath. I work for WL Gore and Associates. Let me first share my agenda for today. After a short introduction, what WL Gore produces, I will introduce you to the product and the process that we're studying here. Then why and how we chose the experimental design that we actually used. And then I want to spend a decent amount of time on the statistical analysis of the results, and then finish with some learnings and a summary. WL Gore and Associates, founded by Bill Gore, is an American company with approximately 10,000 associates worldwide. We have manufacturing sites in the US, East and West, in Germany, United Kingdom, Japan, and in Shenzhen, China. Last year, we ended up with $3.7 billion as annual revenues. Let's see where we're going to end up in this crazy year. And we are privately held, so that means we can make investments with a long-term view and are not driven by proving short-term results, which we prefer a lot. This is a very true statement. Technology is at the heart of what we do. We are a technology, a materials company. And to show you what the bulk of our products are about, it is about fluoropolymer expertise. That's the common link between most of our products. On the left-hand side, you can see some pictures of products or intermediates that are then further put into final products. And on the right-hand side, you can see some SEM microstructure pictures of the membrane, for example. So we modify fluoropolymers in their form and their structure, and we also do things like filling them, coating, laminating, treat the surface and things like that. And we play with the orientation, the density and the thickness and the geometry of the fluoropolymer and put it into different forms like shapes, tapes, fibers, tubes, and membranes, just to give you a few examples. We are probably well or best known for our brand Gore-Tex as the market leader of protective apparel. And you can use Gore-Tex fabrics and apparel not only for hiking, running, but also we protect firefighters, policemen, military, and other workforces. What you may not know is that we are really active in providing stents and artificial veins and heart valves to deal with cardiovascular diseases in tricky cases. And so far we have implanted over 45 million implants to patients and saved a lot of lives. Another big division of our organization is about so-called performance solution. We modify fluoropolymers in ways that they can live in harsh environments to give, for example, mechanical stability, abrasion resistance, chemical resistance, electrical resistance, and other properties. And it's very hard to damage the material. And it's used in a lot of products. Now let's take a look at the product and the process that I want to focus on today. On the left-hand side, you see a vent that is used, for example, in a motor to avoid corrosion. Moisture vapor can get out of this housing through this vent, but water drops don't come in. On the right-hand side, you see a model of the product, and here in green, you see the PTFE membrane, and this is coated with an oleophobic resin. And the job of the oleophobic coating is to preserve the product performance of the membrane in that vent, otherwise it would get stuck with things in the air like oil or whatever is around in this environment where the product is built in. And I want to focus on the making of this oleophobic coating. This is a resin. And now I have a question for you.
There we are. Sorry, camera took a short while to appear there. Maria, thank you very much. Okay, so the next thing we're going to do is run a poll. So this is your chance as the audience to interact and tell us a bit more about your own understanding. So what is your experience level with definitive screening designs, which we've been talking about so far today? Would you say you have none or little knowledge of DSD? Do you understand what they are? Do you have experience using definitive screening designs yourself? Did you invent DSD? And or are you new not just to definitive screening designs, but to the whole thought process behind design of experiments, which is a very different way from how many of us were taught in school how scientific experiments take place. So we are going to give you a little bit of time to answer that question, give you a short while to make sure that we let as many people as possible get those answers in. We have had a question from Shri Krishna Mapuri, who wants to know where they can find the software. Well, that is available as a trial, a free demo trial from JMP's website. So if you Google JMP, JMP, and especially if you Google JMP and design of experiments, you will find their website, and there is a resource there that you'll be able to access for. You can register yourself for a free trial, and that's really the best way to start to get to grips with this. We've also been asked about training courses. So Rahul asked if there's any available course to learn JMP. Now, probably the best thing I can recommend for you from the Chemistry World perspective is that we ran a 5-part Smarter Experimentation for Chemists series. They are similar to today's webinar, where we're looking at software demonstrations and some elements of presentation. You will find that on chemistryworld.com, but I'm also sending a message to the entire audience now with a link to that. So if this has whet your appetite and you'd like to know a bit more, then that 5-part course is a really, really good way to see all of the benefits and the different approaches that designer experiments can offer. Right, I think that's probably enough time for people to vote now. So we're going to close the poll, and straight away, let's share the results. Let's see. So clearly, most people have come here to find out what DSD is, what it can do for them, how it can help you save money, optimize processes, get better results, and communicate your results better. 45% of people have none or little knowledge, and nobody here claims to have invented DSD. So that's good, because we know exactly who it was who did invent it, and so we would know that if one of you was pulling our leg if you claimed to have invented it yourself. 25% do already understand, so here to get a bit more knowledge, but 23% here new to design of experiments itself. Again, that smarter experimentation for chemists course will give you a really good background in that, I think. So let's close down the poll now, I think, and we can carry on with the presentation. Maria, is that sort of what you were hoping to see? Is that the balance of people you were hoping to reach today?
Well, I'm super flexible. I'm a statistician. I'm teaching this to anybody who is willing to learn, so that's fine with me.
Excellent.
But it's good to know.
Okay, well, we will hand you control back now, and you can carry on with your presentation and demo. And we will come back again, get any questions you have into that questions box at the bottom of the GoToWebinar panel, and we'll put those to our speakers shortly. So thanks again, Maria.
Thank you so much, Ben. All right, so let's come to the concrete experiment and experimentation that we are talking about here. Now, the work was to do a so-called process validation of a new reactor. A couple of years ago, we built a new plant for polymerisation. And here, the first step is to do a screening. We want to understand and identify the critical process factors. What are the factors like temperature, pressure, speed, pH, amounts of something, lengths or types of materials that you put in? What are the key players for your process and your product properties? And the second step, once you have identified the critical factors, you move on to find a process setting or a process window in which you reliably are going to produce good product. So in that second step, you need to make predictions about the product performance in your normal production. That means the process validation is a two-step approach. And the screening step, the first one, is if you're new to DOE, you can imagine, let's say, each of those minions represents one factor: temperature, speed, pressure, heat, whatever. And you have so many of them. Your process is complex, way more than you could ever treat in experimentation. And you start picking those that you think are most important, and you want to learn about how they modify your product performance. And let's say you start off with 11 of them, run your screening design, for example, screening DSD, and you find out those 4 are really important and change the properties of your product. So you have identified those candidates, and you only run experiments on a pretty rough level. So many candidates, few information of each one, like in a casting show, right? Each candidate gets only a short period to show what he or she can do. Now, after that, you move on with maybe just 3 of those 4 factors and run an optimization experiment to find your process window, to understand how they interact and how they impact your results. Let's take a look at the process here. We talk about making a resin or a copolymer, and I'm not a chemist, but I learned that if you take 2 monomers, let's call them A and B, and you put them together with some initiators in a organized reaction in a reactor, you turn those monomers into a copolymer. So you build polymer, those chains of molecules, and there's different ways of arranging those molecules, maybe an alternating way or a block organization. And it would of course be interesting to know which one we chose, but this is unfortunately intellectual property, and I cannot talk about that, so you have to make a guess. Now, making the polymer takes 3 steps. The polymerisation, this is where the product is built and made, and also where the product properties get determined. And those 2 steps after that, the so-called coagulation and the drying, are just finishing processes to harvest your product and get it in a good mode. And it's like washing at home. You use a detergent to wash your wash, and then you wash out the detergent and you dry your garments and you're done. It's pretty similar. Now, when the engineer gave me a call, she said, "Hey, Maria, we have a new reactor here, and we heard you do great experiments and you're the best one to help us." And at that moment, I usually get a little nervous as a statistician. So I said, "What is it? What do you need?" So Julia said, "Well, we have 11 factors. Of course, we would love to run center points, so just the low, middle, and high, to learn how things go around our best guess so far. We want to study the interaction, and ideally, couldn't we do the RSM model as well? Because, you know, those runs are really expensive. One experimental run cost more than 10,000 euros. Okay, so I asked, what can you afford? Well, she turned out our budget is just enough to do a screening design, and it has to be as small as possible. So I keep my reaction like this secret, but I sometimes feel a bit overwhelmed. But I tried my best and provided them with a design. At that time, I had heard about the definitive screening designs, and you know already, those have the center points, so not only a low and a high level of a factor, not just the extremes, but also a point in the middle. And for engineers and scientists, this is very attractive. We had 9 continuous factors, so factors that we can change on a continuous scale, like a temperature. You can really set 50 degrees, 60 degrees, or 60.5 degrees, whereas in the categorical factors, you would have maybe ingredient type A and ingredient type B. So we had those 9 factors. We can only estimate a few of the interactions, and we could afford the whole experiment in just 21 experimental runs. Valérie shared already what a definitive screening design is. It is still a screening design, a design to identify the key process knobs. What are the driving factors out of that many, like the many minions? Each continuous factor runs on 3 levels, and to my understanding of design experiments, it is the best in class for screening designs. And especially here in this situation, because it comes with the potential of a bonus. We have the chance to get to a response surface model within the screening design, for which you usually use 2 DOEs and 2 steps, just as I shared in the beginning. Now, then we could make predictions on the commercial product's performance and identify the process window. So for us, in concrete numbers, the potential savings were, we run the DSD with the 21 runs and multiply it with the cost for each one, or we do the traditional approach that would have been 28 runs in a traditional screening design, plus maybe another 20 for the optimization phase. That was the outlook that we had. Let's look at the product specifications. What did we have to meet? The 2 product properties that I picked here out of many more are an MFI, so melt flow index, and TGA, a thermogravity analysis thing. And I won't go into any detail here. We have limits where the property has to land in, and we have the measurement of some residuals. We want to wash out some chemicals that we used to make the reactions going properly, and we want to, of course, minimize those. In those three process steps, we modified factors in all three of them. That is also a beauty about DOEs. Most of our products that we make go through multiple processes, to multiple process steps, and you can change factors in each one of them. It may require some different types of DOE, so you have to be aware, but because this was a simple batch process, one batch of material runs through polymerization, then coagulation, and then drying. It was very simple. In case you're familiar with DOEs, you have no need to run, for example, a split block design. Now, the factors, we changed 2 ingredients. Again, IP reasons don't let me share what those were, and 1 process condition in the reactor. The coagulation is well known in literature, so I'm happy to share the factors we played with, the amount of 2 chemicals, wash cycles, and the wash temperature we used. And for the drying, we played with the dry ramp soak and also with the dry time. Overall, 9 factors. When we had gone through the factors, I discussed that with the 2 engineers. We down selected 11 factors to 9 because, you know, in the end, you need 1 process window to be successful. You don't need to study every potential relationship between the factors and your responses. If you find 1 good spot, that's good. That's enough. One important thing here is the product properties, TGA and MFI, can be measured right after the polymerization. So when we take those samples and measure them, they haven't seen the factors for coagulation and drying. The intermediate residual that we measure has seen all factors of polymerization and coagulation, and for the drying, we measure another 2 residuals, and they have seen all factors active. So to summarize, here for the polymerization, 3 factors active in 21 runs, 2 properties. Here we have 7 factors with 1 properties, and here we have 9. And for the sake of time, I could talk easily 2 hours about this experiment. I will focus on the TGA and MFI analysis. Also, because now that we have only 3 factors used and active, one property of a design, of a definitive screening design, is 3 factors project into a response surface model. So if you have only 3 active factors, you can do that response surface model design. That means you can find your process window. And this is what we could do. And this is what saved us a second experiment. Now, let's look at the plan, the run sheets, and the results. I have colored the factors, the 3 poly factors, those ingredients and the condition, then the coag factors and the 2 drying factors along with all the results. And if you know a little bit about statistics and DOE, the MFI and TGA were really nice and friendly and analyzable responses on a continuous scale, whereas for the residual, by nature, you would expect you want to see no residual in your product, right? You want to get rid of the residuals. So for example, in the final residuals, we had a lot of 0.05s, which means that was below the detection limit of 0.5, which is great for the product, but for the statistical analysis, this is a difficult distribution to analyze. But if you have a statistician, he or she should be able to deal with it. I have put all the results together to save time, although it's super easy and quick to click around and jump. For the MFI, we have those specification limits and the target. And from all 21 results, you can see already, well, we have a good bunch landing within the specification limits and also results outside of the specification limits. Same for TGA, who everything pretty close to the upper specification limits, with a few that went over the top, but again, a good amount, around 5% were outside of the specification limit. So there is hope that we can see something. And the reason why I look at that distribution is also to do a plausibility check on the data and get a first feeling for what to expect. Now, the scatter plot matrix is a very simple graph to just, in a visual way, plot the 3 active factors for the polymerization against the 2 responses that were measured afterwards. And the red lines are just to help a visual aid for your eyes. And you can see the big player definitely is that process condition. The 2 ingredients don't change much. And they go in the impact of the process condition goes in different direction for each response. Okay, now what is a good process setting? For that, we are looking into a response surface model that I have fitted already. And in this effect summary, that is a great summary of all the effects in your model, so your main effects, your quadratics, and the interactions for those 3 factors. You get an overview for both responses overall. What is the importance of the factor? And you can see that process condition is pretty overwhelming. Everything else is of minor importance to the results of the MFI and the TGA. For example, this one is even insignificant, but I'll leave it where it is. On the prediction profiler that Valérie also has shown already, that is a great tool to understand the behavior of the factors. And what I've done here already, it gives you a maximum, the best setting. So there is something called a desirability function. And for example, for the MFI, I have a target, and I can say here, that is the maximum desirability for the result of MFI. And JUMP will come up with a proposal of a process setting for which the MFI is optimum. So I maximize the desirability here. And it does it in the same time. It also takes the TGA optimum into account and finds a process setting that is best for both MFI and TGA, although they are a bit contradicting with regards to the temperature, to that process condition. Now, the ideal setting that is proposed is use 6.5 of that ingredient, whereas they are not really significantly different from each other, whether you use a few or a lot. But here that process condition is really important. There is a very nice way in the contour profiler, again, a very rich graph. Here you can visualize the process window. I can pick 2 of my factors, and I chose the most 2 important ones, the process condition and the ingredient number 2. And in the white region, I will meet my product specifications, whereas in the reddish shaded region, I will fail the MFI specification limits. I will be out for the MFI. So this is a topographic visualization, a response surface picture of those responses. And for the TGA, there is no gray shaded area. So within whatever I choose here for this process setting and for this ingredient, I will be in spec for this product. So success in this case for the polymerization where the product properties are set within that one-shot design, we could find good properties and a good process window. So it's not only that you save time and money, you also learn about the behavior of your factors in a way that is, to my experience, really hard to gain in other ways. And for the final residual, you could look into complicated stuff like that binomial generalized linear model. I will skip that because the analysis of a DSD, because at that point you have all 9 factors active, is tricky, it is sophisticated, but I have a very simple learning from the residual in the end, how that went. So after playing with the data, there was one way, in a very descriptive way, where you need no statistician for you to do that. When you just look at the number of wash cycles and the final residual, how much is left in the product. So if you only use 3 wash cycles, you will find some chemicals left in your product. But if you take more than 5 wash cycles, so we really took 5.5 here, no residuals left, and with 8 also. So we knew with 6 wash cycles we should be good, which was a great finding. Now, in general, when you think, when is a DSD appropriate? It is appropriate if you are in the screening phase. You want to identify out of many factors the key ones. If you have just 5 factors, you better choose a different design. If you have mostly continuous factors, you can leverage the gain of the center points, which you also don't get in traditional screening designs. It bets on the factor sparsity, so only a few actors should be active, which most of the time is the case, and you don't learn that much about many interactions. So there is some pros and cons with it. For us, it really paid off. We really did save that follow-up experiment, and the DSD was shorter than in the traditional approach, the first experiment we would have taken. To summarize, for us, the definitive screening design that JUMP came up with a couple of years ago was really efficient and effective. We saved that second experiment. The analysis in DSD is and may get sophisticated, and you have to deal with the shortage as in screening designs. Usually you ask a lot of questions, you have a lot of hypotheses to test, and if only a few are active, you're good. If not, you don't learn that much. With that, I want to finish and thank you for your attention.
Thank you very much, Maria. So we've had plenty of very interesting questions, and let's get Valérie back as well. And while Valerie's just joining us, I had a question from Wayne who asked if it's possible to get hold of the data to try some alternative analyses. And we're not going to share the data that you've seen today, but if you go to that, the 5-part course I was talking about earlier, and again, I will share the link with the audience now. So it should be a new link landing in your GoToWebinar box now. That's for our design of experiments page, which not only has a link to that 5-part course, but also that course had homework examples along with it, where you have data sets in JUMP files that you can play with. So Wayne, if you want to experiment with different ways of analyzing that data, then those homework files are probably the best thing for you to try. So thank you, Valérie, for joining us again. One question that came up on at least 3 different occasions, so Pavel, Paul and Mohammed all asked, is it possible or is it reasonable to run a definitive screening design with 1 or more categorical factors? And I think this is something that comes up quite a lot. So when we have non-continuous factors, is a DSD still the appropriate way to look at that?
Yes, you can easily handle with 1, 2, maximum 3 categorical factors. Often you have the bulk of factors usually is continuous, but you can easily have a couple of categorical factors.
Excellent. Thank you very much. So Varun asked, how do DSDs compare against custom design experiments, which you can also run in DV? What additional benefits do they have? Valérie, is that something you've got a comment on?
So the question was, what is the differences, or what are the benefits of custom designs versus DSD?
Yes.
Yes. Well, in custom designs, you have, of course, a lot of different properties, like if you have problems in different types of formats of factors, so you can actually build designs with a mixture of factors, with categorical, with numerical, with blocking factors, as you don't have in custom in DSD. You have also the power to say, I'm only allowed to do only a certain numbers of runs, as you don't have in DSD. And also, if you have problems in runs that may fail because typically certain levels of factors will not be feasible, in custom designs it's also possible to do that you don't have in DSD. Maybe Maria, you have lots of other comments.
Yes, can't wait. Yes, so actually the example that I showed, the other one, the traditional, was a optimal design. And the optimal design in JUMP is like the hybrid. You can do anything with it. And the DSD is a very special type design. And in the optimal design platform, in the custom design platform, you can really set your model. You can pick, for example, I want those 4 two-factor interactions. And for this 1 factor, I'm not interested in the linear, non-linear effect. I skip the quadratic effect. You can really model your model. And it's a very general thing, and it is like the go-to platform and type of DOE if you cannot apply a DSD. But that specific type of picking the model and putting things together requires more runs, a larger design size.
Speaking of which, how many factors would you say are typical, or a typical number of factors for a screening phase? You said at the beginning, you said in your conclusion, this is ideal where you have a large number. What do we mean by a large number?
Definitely more than 5. Yeah, at 5 and 6 and 7, I usually do a comparison between different designs and compare their performance. Is the 6-factor design, is that better and shorter with the DSD, or do I switch to optimal design, for example, different optimality criteria given on what I want to learn. But up to 6, 7, I may check, but after that, definitely that is good for a DSD.
Perfect. Well, so, and in your example, you said you went from 11 factors initially, you settled on 9. What was the reasoning behind that?
Yeah, so in a design experiment, it is like a marriage between the technique of using a DOE and the subject matter expert knowledge. I would never want to set up a DOE myself, but really talk through the process with the engineers. I need to understand the process as a statistician to provide with the best design possible. And when we talked through all the factors, we learned that those 2 factors probably will have a similar effect than something else. So there might be, like what Valérie also showed, a factor correlation. If one factor has the same effect on the results like another one of them is good enough. And we knew with those 9 factors, we would have enough chances to find a good process window.
So if you've seen, for example, that the effect of increasing temperature and increasing pressure is exactly the same, then you only need to run your experiments with one of those 2. Excellent. Thank you very much. We're very nearly out of time, but I'd like to say a huge thank you to Maria and Valérie for joining us. It's been a fascinating hour. We've covered a lot of space. So for those of you who have joined us today, do go back and watch that recording. I'm sure you'll pick up on bits that you missed. We've packed a lot into the last 60 minutes. And thank you to all of your questions. A huge thank you to Jump as well. So Jump, we work with quite a lot. They have supplied us with excellent guests like Maria and Valérie, and excellent resources on our website like the ones that we've already shared. If you'd like to carry on learning more about Jump and what it can do for you, then join us for another webinar almost this time next month, September the 1st, to learn about how Synthace's software platform Anther empowers scientists to automate design of experiments for optimizing their bioprocesses. And you can find that online. Again, go to chemistryworld.com/webinars. You'll find it there, but I will also fire out a link again in the GoToWebinar chat box. You can go and register for that straight away, and we look forward to seeing you there. So thank you once again to Jump, to Maria, to Valérie, to all of you for attending.
Welcome. Thank you.
And keep an eye out for your certificate of attendance, which will be with you in a few days' time. I'm Ben Valsler, Chemistry World's digital editor, and we will see you for the next Chemistry World webinar very soon. Thanks again.